Hello and welcome to a quick screencast showing how to determine the temperature from intensity data. What I'll be doing here is reviewing the tutorial 4 data set where we use the intensity from the dominant spectral series, but the approach is equally relevant to the second homework assignment. Here we can see the equation that relates the population in the J state to the population in the ground state. Notice that in the exponent here, my rotational constant is assumed to be in Hertz. And you remember that during the tutorial, we were calculating the rotational constant in Hertz. If, however, the rotational constant was in wave numbers, as it is in the homework assignment, then I would also need to multiply this numerator by the speed of light in centimeters per second. The reason why is that for any exponent, it must be dimensionless, which means that the numerator must have the same units as the denominator. KT has units of joules, and so I must ensure that the numerator equally has units of joules. So as I said, the intensity of any spectral line is proportional to the population in each state. So if I substitute in this expression for the population in this J state, then we have this expression here. But this is a relationship of proportionality. And in order to do the minimization, I need to include a constant of proportionality. This is where the factor A comes from, the parameter A. So let's use this final equation here in order to determine the temperature that was measured in that interstellar dust cloud that we looked at in tutorial 4. It should be noted that the data, the spectral data that we had was, of course, an emission rotational spectrum. And so therefore, we were looking at the rotational lines for transitions from J equals 1 to 0, 2 to 1, etc. So the 5 spectral lines, the initial J state was 1, 2, 3, 4, and 5. Our observed intensities, at least the ones that I measured for the spectrum that I had, were 17, 43, 69, 103, and 92. Right, well now I need to have my calculated value for the intensity. And for the calculated value of the intensity, I use this model expression here, and I use trial values for the temperature and the constant of proportionality here. So let's introduce our model expression. It will be equal to A1 protected times 2 times the initial J state plus 1 times the exponential of minus 1 times H times B times J into J plus 1, close brackets, all over K times T. Okay, so press return. That's my initial guess. Let me auto-complete. Now, in order to do a minimization to determine the best values of temperature and the constant proportionality that fit this observed data, I need to determine chi-squared, which you'll remember is the sum of the squares of the residuals. So let's calculate first the squares of the residuals for each of the 5 observations. So this will be equal to the observed, is equal to the observed intensity minus my calculated intensity squared. I'll autocomplete for the 5 lines. And then in this yellow box, I'm just going to make this the sum of those 5 residuals. There we go. Okay, now what I want to do is minimize this value using Solver to optimize these 2 parameters. So let's go to Solver, and I need to set this to be the chi-squared, and I want to minimize this data, and I want to do it by changing cells B4 and B5. One of the awkward things about Solver is that it checks this box here, make unconstrained variables non-negative. This needs to be unchecked. For some versions of Excel, this will lead to unrealistic solutions where it hasn't actually optimized the system and will give you a temperature that is nonsensical. With that unchecked, then I can click Solve, and then we can check the results. And here we go. So it has managed to minimize down to a chi-squared value of about 608 by creating or by using a temperature of around about 95 Kelvin and a value for the constant proportionality of around about 10. We're not interested in the constant proportionality, but we are interested in that temperature. 95 Kelvin for an interstellar dust cloud is towards the upper end of the temperature for an interstellar dust cloud, but is quite reasonable. Thanks for listening.